Good morning, everybody. Hope everyone's doing well. This is the lecture starting equilibrium. Yeah, we're just going to go for a while and see how far we can get. We're kind of done with kinetics. Make sure you start working through those problem sets, but it's all posted on Google Classroom. All right, so today we are going to start chemical equilibrium. And I guess we should start by defining. And when we're in a chemical equilibrium, the state where the concentration of all reactants and products remains constant with time. So once we're at equilibrium, the concentration of reactants and products is constant, which means the rate of the forward process is equal to the rate of the reverse process. Okay. So algebraically, this would be an equilibrium. So what this is saying is A plus B is producing C plus D, but at the same time the reverse reaction is happening and C plus D come together to produce AB. Now this right here, these double arrows, this means that it's at equilibrium. Right? Another way we can look at it is the rate of this forward reaction is equal to the rate of the reverse reaction. If these rates are equal, the amounts of each one of these are not going to change, and we're going to talk more about that. All right, now, double arrows. This is the double arrow I think I mostly use. There are other ones that you'll see. All right, you might see this one. You might see that one. I suppose you could see this one. Okay. I don't care which one you use, but all right, make sure you just understand that the double arrow means it's at equilibrium. All right, now what I want to do is I kind of want to go through what happens from the beginning of a reaction until we reach equilibrium. So so at the start of a reaction, we have A plus B, and at the very beginning, there are no products. Okay. We're going to have a high concentration of A and B. Now, if we have a very high concentration, that tells us something about our rate. All right, we're going to have a relatively fast rate of reaction. Now, at this point, there is no product, which means there is no reverse reaction. Right? So this cannot be at equilibrium. Okay, so over here, we're going to have a very fast rate for my forward reaction, and at the beginning, there is no product, so there is no reverse reaction. All right, so this is not at equilibrium. Well, once we let this reaction start, so as the reaction progresses, we start to form some C and D. So what's happening as the reaction goes, the concentration of A and B is going to decrease because these are going to come together to produce these products. So over here, my concentration is going to decrease. And as this concentration decreases, my rate decreases. Over here, the concentration of my products is increasing. And once we have some products, the reverse reaction can start. All right, so my reverse reactions start, but the concentration to start is very, very low. All right, and as we produce more of this, all right, our concentration increases, which means our rate is going to slowly increase. Okay. Again, we are not at equilibrium yet. Okay, we're not at equilibrium, but you can kind of see what's happening. All right, the concentration of these are going down, and my rate's going down, 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 down. Over here, my concentration of these is going up, and my reaction rate's going up, 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 up. All right, so this one's going to keep coming down, this one's going to keep coming up, and eventually the rates become equal. And at that point, we have reached equilibrium. So at equilibrium, okay, once we've reached equilibrium, our concentration is constant on both sides. Okay. If our concentration is constant, the rate of the forward is equal to the rate of the reverse. I also want to look at this graphically, and we've actually kind of already done this, but I'd like to put it in here again because it is important, right? And they do sometimes like you to look at these graphs and say, hey, what are we at? What's going on? All right, so let's look at a graph here. We'll look at 3 different graphs. Each one, the bottom is time. All right, this is concentration for this one. This one's also concentration. But this one I want to look at rate. Okay, so just be careful with this one. All right, now what I'm going to do is, let's write a key here. I'm going to use a solid line for reactant and a dotted line for product. All right, so for my first one, all right, our concentration of reactant starts very high, and as the reaction progresses, it goes down, 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 and levels off. All right, for our product, it starts low. Matter of fact, it starts at 0, and it does the opposite. Okay, up, 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 up. Okay, now, all right, where does this reach equilibrium? Well, probably somewhere in here. It's not perfect. It's not perfect. All right, where the concentrations have leveled off and are constant, this is where we reach equilibrium. It's not where they touch. All right, remember, at equilibrium, the concentration of reactants and products is constant. They're not equal. Well, they can be, but usually they're not. The amount of product and reactant generally are not equal. Right? Now, we could have something like this. All right, our reactant can start high, and it can level off pretty quick. And again, our product starts at 0, and it can level off pretty quick. Okay. They don't meet. That's okay. All right. Remember, the amounts don't matter. It's that they're not changing. So where does this one reach equilibrium? Probably somewhere in here-ish. Now, these graphs are concentration and time. All right. Be careful when we have rate versus time. Because in this one, okay, what is this going to look like? Well, at equilibrium, the rate of the forward is equal to the rate of the reverse. All right, so these have to meet. Right? So this is going to do something like this. And the reverse is going to do something like that. Right? And then they stay the same. Okay, where does this reach equilibrium? This reaches when they touch. Okay, so this is where we're at equilibrium. Right, so just be careful with your graphs, because these will pop up. All right, really what you have to concern yourself is, do you have concentrations or do you have rates? Okay. All right. Let's get into the meat of some of this. All right, so in a chemical reaction, the actual concentration of reactants and products at equilibrium are dependent on the initial concentrations of the reacting mixtures. So let's say we have a reaction A plus B going to AB, and this comes to an equilibrium. All right, so let's say the first time I do it, okay, I'm going to look at concentration of A, concentration of B, and concentration of AB. And we're going to look at the beginning of the reaction and at equilibrium. Okay, so if we start with a 1.0 molar solution and a 1.0 molar solution of A and B, okay, and none of AB, okay, this reaction will, at equilibrium, these are going to go down, this is going to go up. And we might measure and get a concentration of 0.5 molar, 0.5 molar, and 0.5 molar. Right? But these concentrations at equilibrium are dependent on where we're starting over here. Right? They're dependent on what we're starting over here. Right? Now I want to contrast this, so let's just change a couple things in our second trial. So this is at the beginning and at the end at equilibrium. Okay, so let's say this time we start with a 5 molar solution of each one of these. Okay. This goes down to 2.5. This goes down to 2.5. We're starting at 0 still with this. All right, when we look at this, it's the same reaction, this ends up being 12.5 molar. And we'll see where that number comes eventually, right? But you can see that your concentrations at equilibrium are going to really depend on where we start. So here we started with 1 molar, all right, and we end up with half. So at equilibrium, we have 0.5 molar of this, 0.5 molar of this, 0.5 molar of this, all right? Over here, we're starting at 5 molar, ending at 2.5, but we get a concentration of 12.5 molar. So it really depends on where we start with, what our concentrations at the beginning of the reactions are. Okay? So the concentrations here of each trial are different. But there's a relationship that is the same for each trial. And that's where we're headed. Okay, we're going to talk about this relationship here. So this is called the law of mass action, or the equilibrium expression. All right, so here we go. Concentration of all products multiplied together divided by the concentration of all reactants multiplied together will be equal to a number called the equilibrium constant. And of course, we use K. Okay, we have rate constants. This is going to be an equilibrium constant. Now, K is dependent on the specific reaction and the temperature at equilibrium. So this K is a constant for every specific type of reaction, and it changes depending on temperature. All right, now we have something called KCs and KPs. Kc is the equilibrium constant when using concentration. K sub P is the equilibrium constant when using partial pressures of gases. But in reality, they work the same. And you'll see what I mean as we work through here. All right, so now, how do we come up with this equilibrium expression? Well, let's say that we have an equation. Coefficient little a to first reactant plus coefficient little b, big B for our second reactant in equilibrium with, let's use little p for P plus N for big M. Now, to write this expression, all right, let's say we're dealing with concentrations, Kc is going to equal the concentration of P to the P times the concentration of N to the N divided by the concentration of A to the A and the concentration of B to the B. So this is our general formula for our equilibrium constant. So now what I want to do is I want to go back and I want to apply this to this reaction right here. I want to apply this right here. Okay, so what we're going to do is we're going to use this data in a minute. All right, we're going to actually calculate our equilibrium constant. Okay. So we go back to A plus B. It was in equilibrium with AB. Okay, our equilibrium constant, our Kc, would be the concentration of concentration of AB, and it's a 1 here, so this would be a 1, all over the concentration of A, and again, that's a 1, so this is a 1, times the concentration of B. Okay, so there's my equilibrium expression. All right, now we can substitute this. We can substitute now our concentrations in here. All right, so we have these. We can actually calculate Kc. All right, so for our first trial, okay, our constant would be equal to 0.5 molar divided by 0.5, 0.5, right? When we do this math, Kc is equal to 2.0 moles per liter. Now, what I want to do is I want to do the same thing for my second trial. What should my K be? Okay, should be the same thing, right? It's the same reaction at the same temperature. We're starting with different amounts, but my equilibrium constant should be constant. So in this case, we have 12.5 molar divided by 2.5 times 2.5 molar. When you do this math, we again get 2.0 molar or moles per liter. All right, so my concentrations are different, but my equilibrium constant is the same for the reaction. Okay. All right, and we'll be able to use this math to do some things. Why don't we go ahead and write the expression for this equation? write the equilibrium expression. So we have H2 plus Cl2 gas going to 2HCl gas. So Kc is equal to the concentration of HCl, right? But it has a coefficient, so that gets squared, divided by the concentration of H2 times the concentration of Cl2. Right? So the coefficient becomes the exponent. In the expression. Now, there's another step that we have to take. In a reaction with pure liquids and solids, for example, maybe we have distilled water, or just pure ammonia, or solid we might have, I don't know, a chunk of gold or a chunk of copper, right? In these two cases, these things are not mixtures. And they don't have concentrations, or their concentrations don't change. Okay. So for solids and liquids, these are not included in the equilibrium expression. And that's important. Or that. Okay. So let's come up with an equilibrium expression with this instance. All right, so let's say we have CH4 gas plus 2O2 gas in equilibrium with CO2 gas plus 2H2O liquid. All right, so we do the same thing. We're still going to use our same expression formula. So our Kc is equal to the concentration of our products. All right, this doesn't count because it's a pure liquid. It really doesn't have a concentration. So this is the only one that we use in the expression. So we have the concentration of CO2 gas. There is no coefficient. It's a 1. Divided by, we use both of these because they're both gases, the concentration of CH4 gas. Again, this is a 1. We could put a 1 there. Times O2 gas. And this does have a coefficient, so this would be 2. So this would be my equilibrium expression for this guy. And we could calculate our K if we had some concentrations. All right. What I want you to do is I want you to write the equilibrium expression for the combustion of propane. So stop the video. I want you to go ahead and do the problem. All right, you're going to have to write the equation and come up with the equilibrium expression. All right, then turn the video back on and I'll do the problem for you. Okay, so hopefully you've done it. All right, so here's my balanced equation. The formula for propane is C3H8, and it's a gas, plus 5O2 gas, and that will be in equilibrium with 3CO2 gas plus 4H2O, and that will be a gas. Okay, so there's my equation. Hopefully you came up with that. Now Kc would equal the concentration of CO2 gas cubed times the concentration of H2O to the fourth, all over the concentration of C3H8 gas. That's a 1 times the concentration of O2 gas to the fifth. And that would be my equilibrium expression. Okay. So I want to look at, there's a relationship between the forward and the reverse reactions. Okay, so there is a relationship between the equilibrium expression of a forward and reverse reaction. All right, so let's explore this a little bit. Let's say that we have this equilibrium occurring, O2 gas plus 2 SO2 gas in equilibrium with 2 SO3 gas. Okay, so let's look at my forward reaction first. Okay, so if we calculate our equilibrium expression with the forward reaction, Kc is going to equal the concentration of SO3 squared all over the concentration of O2 times the concentration of SO2 squared. Okay. Now, let's look at the reverse. Okay, for my reverse reaction, this whole thing is just boop. So we have the concentration of O2 times SO2 squared all over the concentration of SO3 squared. Okay, so how are these related? Well, we often will do this. We'll call the forward reaction Kc, and we'll call our reverse reaction Kc prime. All right, so how are these related? Well, Kc and Kc prime are just inversely related. So we could write this way. Kc is equal to 1 over Kc prime. All right, this is going to make things easier down the road. So if a chemical reaction is reversed, the value of the new equilibrium constant is the inverse of the original constant. In other words, if I know Kc, I can calculate the reverse reactions Kc prime, right, just by doing its inverse. Okay, and we'll need this for another step. Okay, let's try this. What if we multiply or divide coefficients by a constant? Let's try this. So sometimes we'll have to change our coefficients, and you'll see why later on. So let's say we have this reaction again, O2 plus 2SO2, these are gases, in equilibrium with 2SO3 gas. All right, and we already came up with Kc here. Kc was equal to the concentration of SO3 squared all over the concentration of O2 times the concentration of SO2 squared. Now, what if for some reason we had to multiply this whole thing by 3? And we might have to do this. This might be, and the reason I'm saying this is this might be an elementary step. And we end up adding elementary steps, and we've talked about that. So in some cases, we might have to change the coefficients. The ratio stays the same. So let's say if we multiply this whole thing by 3. Okay, so if we multiply through by 3, we end up with 3O2 plus 6SO2, and these are still gases, in equilibrium with 6SO3 gas. All right, so what does this do to K? And let's call it K double prime C. Well, it changes it to SO3 to the 6th all over O2 to the 3rd SO2 to the 6th. Or we can write this a different way. All right, we can write this a different way. So instead of doing this, we multiplied by 3. All right, so we can take our original Kc and really what we're doing with this mathematically is we're cubing it. All right. So what this is really saying is if we want K double prime C, it's going to equal Kc times Kc times Kc. Okay, we're cubing this thing right here, which is going to equal really Kc cubed. So this is just, in the long run, it's going to make it shorter for us. So we can write this again. The equilibrium constant is raised to the power equal to the factor multiplied. Well, this is if we multiply. What happens if we divide? What if the equation is divided by 2? Well, what's another way to divide by 2? It's the same thing as multiplying by multiplying by 1/2. All right. So what would our KC be if we divide it by 2? Well, let's call this triple prime because we're taking our KC and we're changing it for a third time. All right. It would equal our original SO3 squared all over a concentration of O2 times the concentration of SO2 squared. All right. And what are we going to do with this? We're going to raise it to the 1/2. Well, mathematically, what are we doing here? Well, mathematically, we're really doing this. We're taking the square root of the concentration of SO3 squared all over the concentration of O2 is the concentration of SO2 squared. All right, so mathematically what we're doing is we're saying K triple prime C is equal to K C to the 1/2, or we could just rewrite it the square root of our original equilibrium constant. Okay. All right, how do we apply this? Let's try just a quick little problem. Let's talk about the manufacturing of ammonia. So NH3 is manufactured using what's called the Haber process. Okay. And what we're doing is we're taking N2 gas plus 3H2 gas, and it actually will form an equilibrium with 2NH3 gas. So now, let's say we're at 130 degrees C. Okay, at 130 degrees C, we have some equilibrium concentrations. So the concentrations of NH3 is equal to 6.2 times 10 to the minus 2 molar. And let's just write equilibrium concentrations. And the concentration of N2 is equal to 1.70 times 10 to the minus 2nd molar. And the concentration of H2 is equal to 6.2 times 10 to the minus 3rd molar. All right, let's calculate the Kc. So our equilibrium constant would equal the concentration of ammonia squared all over the concentration of N2 times the concentration of H2 cubed. So we plug in our numbers to get our constant, and we end up with 6.2 times 10 to the minus 2 molar squared divided by 1.70 times 10 to the minus 2nd times 6.2 times 10 to the minus 3rd, and that is cubed. And we do all this math, and Kc ends up equaling 9.5 times 10 to the 5th. Okay, this Okay, this is my equilibrium constant. Kc has no units. Okay, our equilibrium constants do not have units. So we end up with an equilibrium constant of 9.5 times 10 to the 5th. All right, now, let's calculate K prime C, or Kc prime. And the prime is telling me the reverse reaction. Well, I can go through and actually put all these numbers back in. Remember, this is just inversed. Or I can just say this. Look at Kc prime is equal to 1 over Kc, or 1 over 9.5 times 10 to the 5th, or 1.1 times 10 to the minus 6th. All right, so it's just an easy way to calculate the equilibrium constant for the reverse. Now, what if we have to change this? What if we have to change our coefficients, and otherwise we're multiplying or dividing? So let's calculate K double prime C at 130 degrees for the following. 1/4 N2 plus 3/4 H2 is in equilibrium with 1/2 NH3. Okay. What have we done from our original? What have we done from our original equation? So our original equation was N2 plus 3H2 was in equilibrium with 2 NH3. Well, to go from here to there, we multiply by 1/4. Okay. Well, we know what to do with that now. Our K double prime C is equal to our original Kc raised to the 1/4 power. So we go 9.5 times 10 to the 5th to the 1/4, and when we do that math, it turns out to be 31. Okay. Now, we're going to need each one of these, and sometimes they get combined. We're going to do lots of different things in the next step. But for today, that's where we're going to stop. All right? So I will post this. It'll be on YouTube with a link on Google Classroom. I do have a bunch of work for you to do. All right, so please look into that, and I will talk to you again soon. Have a great day.